Hello there. Today, our group will be explaining about one of the key concepts in chemistry. As you can see on the slide, there is a swing. So, say if there's a person pushing on the swing, the swing would move forward and backward. So it would go like back and forth, but then eventually it would return back to its original position. Well, this analogy aligns with our topic today, which is Chatellier's principle. This principle explains what happens when a system at chemical equilibrium is disturbed. Or, in simpler terms, it is when a change is applied to a system at equilibrium. The equilibrium would shift or adjust itself. This is to minimize the effect of the change and then eventually restore the balance or the equilibrium.
There are three main factors that affect equilibrium. 1. Concentration. If we add more reactants or products, the system shifts to use them up. 2. Temperature. Increasing temperature favors the endothermic direction, while decreasing temperature favors the exothermic direction. 3. Pressure. For gases, increasing pressure favors the site with fewer gas molecules, while decreasing pressure favors the site with more gas molecules. Let's go into each factors one by one, starting with concentration.
Here's an example using hydrogen and iodine reacting to form hydrogen iodide. If we increase the concentration of hydrogen or iodine, equilibrium shifts to the right, producing more hydrogen iodide. But if we increase the concentration of hydrogen iodide, equilibrium shifts to the left, producing more hydrogen and iodine. If we decrease hydrogen iodide, equilibrium shifts to the right again, forming more hydrogen iodide to replace what was removed. So the system always tries to oppose the concentration change.
Next, let's talk about how temperature affects the Haber process. The balanced equation is nitrogen gas plus 3 molecules of hydrogen gas gives 2 molecules of ammonia. And since the enthalpy change is negative, the forward reaction is exothermic. So what does this mean? If we increase the temperature, the system will try to oppose that change by favoring the endothermic direction. This shifts the equilibrium to the left, producing more nitrogen and hydrogen instead of ammonia. On the other hand, if we decrease the temperature, the equilibrium shifts to the right, which favors the exothermic forward reaction. This means more ammonia is formed. In short, heating works against ammonia production, while cooling helps produce more ammonia.
Now let's look at pressure, which only affects gaseous reactions. For example, N2O4 is in equilibrium with 2 moles of NO2. On the left, there's 1 mole of gas. On the right, there are 2 moles of gas. If pressure increases, the equilibrium shifts to the left towards fewer moles of gas. If pressure decreases, equilibrium shifts right towards more mole of gas. If both sides have the same number of gas molecules, pressure change has no effect.
Finally, let's take a real-life example that everyone's familiar with, a soda can. The equilibrium here is between carbon dioxide gas and carbon dioxide dissolved in the liquid. Inside a sealed soda can, the drink is kept under high pressure. This pressure pushes the equilibrium to the right, which means more carbon dioxide dissolves in the liquid. That's what keeps the soda nice and fizzy. But the moment you open the can, the pressure above the liquid drops. Now, equilibrium shifts to the left and more carbon dioxide escapes as gas. That's the fizzing sound you hear when you open a can of soda. So to wrap it up, Le Chatelier's principle shows us how equilibrium systems respond when conditions change. They shift to oppose the changes in concentration, they adjust to temperature changes, and the balance changes in pressure.
The effects of pressure equilibrium has. In a closed system, such as our bottle of Coke here, Carbon dioxide gas is in equilibrium with carbon dioxide aqueous. When the bottle of soft drink is open, which is our Coke, the carbon dioxide aqueous is shifted to the left to keep the partial pressure of carbon dioxide gas constant.